Welcome back to linear algebra. In this video, we are going to be discussing the inner product. Just as we've worked to extend the idea of a vector space from the Euclidean vectors into more general spaces and looked at ways of looking at things that look kind of like Euclidean vectors but have different operations, and capture all of that under the same umbrella of a vector space. It's nice to have some other operations. In Euclidean vectors, we have the dot product, which allows us to define an angle between vectors. It allows us to define a magnitude and several other tools. And we can have that or something like it in other vector spaces as well. We call that thing an inner product. So without further ado, let me get my head out of the way and let's dive in with the definition. So let's let V be any vector space. We will define an inner product on V as a function which maps a pair of vectors little u and little v to some real number, which we will denote using these angle brackets. So angle brackets, vector u comma vector v, is read as the inner product of u and v, and it is a real number that has four properties associated with it. We have a symmetry property, which tells us that the inner product of u and v must be the same as the inner product of v and u. The order doesn't matter. The inner product is commutative, essentially. We have additivity, which is essentially going to be a distributive property. If we have u plus v with w, that's the same thing as the inner product of u with w plus the inner product of v with w. We have homogeneity, which is essentially an associative property with scalar multiplication. The inner product of some constant k times u with v is the same thing as that constant k times the inner product of u and v. And finally, we have a property which is called positive definite or positivity, or a couple of different names similar to that, which tells us that if we take the inner product of any vector with itself, we are going to get a non-negative number, something greater than or equal to 0. And furthermore, the equals 0 case can only occur when the vector you are looking at is itself the 0 vector. So these four properties, these four axioms, are the definition of an inner product. And if you have a vector space with which you have equipped an inner product, you now have what we call an inner product space. And having an inner product space allows us to do a couple of additional things that we couldn't do with vector spaces otherwise. Before I get to some of those things, I want to go through a couple of properties. I said in the intro to this video that the inner product space was supposed to be a generalization of the Euclidean dot product. So the dot product forms an inner product. It satisfies these properties. And when you equip Rn with the usual meanings of vector addition and scalar multiplication, along with the inner product in the form of the dot product, you get an inner product space called the Euclidean N space. I'm not going to go through and prove this because I actually already did. If you go back in your notes or go back to an old video where we were first talking about the dot product, you will see that we looked at the properties of the dot product and we saw that all four of these properties hold true. So we already have a inner product space that we know how it works and we know what works with it. And one more general theorem about inner product spaces before we get into some of the fun stuff. Forgot what I was writing. I didn't put enough vectors there. Let V be an inner product space. Let U, V, and W each be vectors in that space. And let K be any real number. then with just that, we have several other algebraic properties. The inner product of u with kv is the same thing as k times the inner product of u and v. We have that the inner product of u with v plus w is equal to the inner product of u with v plus the inner product of u with w. We have the inner product of u minus v with w is equal to the inner product of u with v minus the inner product of u with, I'm sorry, I'm writing the wrong line down. This should be the inner product of u with w and the inner product of v with w. I was starting to write down the next line where we start with the inner product of u with v minus w. And that's where we get inner product of u with v minus inner product of u with w. So these couple of theorems are very easy to prove using the general properties of the inner product space. I'll work through the proof of the first one, and I encourage you to try the other ones on your own. They're not that challenging, I hope. But if we take the inner product of u with kv, we know by symmetry that this is the same thing as the inner product of kv with u. And we know by the homogeneity property that this is the same thing as k times the inner product of v with u. And then using the symmetry property once again, inner product of v with u is the same thing as the inner product of u with v. And using the same amount of logic, you should be able to get through the other three properties with fairly straightforward proofs there as well. All right. So we know that inner product spaces exist. We know that we are able to work with them if we can find them. Now it's just a matter of looking for inner product spaces that might be interesting. For the moment, I'm going to stick with the Euclidean vector space and look at a slightly different inner product. This is called the weighted average inner product. And in general, it tells us that if we simply multiply each of the entries, so if we take the inner product of u with v, and we have some a1 times u1 v1 plus some a2 times u2 v2 all the way down, you get a different inner product in Rn. And it's possible to prove that in general. It's not that challenging to prove it in general. But let's take a look at a specific case. How about the case of the inner product with u and v is u1 v1 plus 2 times u2 v2 plus 3 times u3 v3. The calculation is a little bit strange, but once you start to see how it works, it makes sense pretty quickly. So if I want to take the inner product of a couple of vectors, say 1, 4, -2, and 2, -1, 5, that's going to be 1 times 2 plus 2 times 4 times -1 plus 3 times -2 times 5. So that's 2 minus 8 minus 30, or -36. But with this inner product, we can still look at the properties and make sure that it actually holds. So if we want to prove that this is an inner product on R3, in order to do that, we want to look at those 4 properties. We want to look at the inner product on VU, which is going to be V1U1 plus 2 V2U2 plus 3 V3U3. And then using the commutative property of real numbers, since these are all real numbers, this is the same thing as U1 V1 plus 2 U2 V2 plus 3 U3 V3. And that is definitely what we get when we take the inner product of U with V. We want to look at additivity. So we want to take the inner product of U plus V with W. So that will be U1 plus V1 times W1 plus 2 times U2 plus, that's not a plus V2 times W2 plus 3 times U3 plus V3 times W3. Using the distributive property of real numbers, this is U1W1 plus V1W1 plus 2 U2W2 plus 2 V2W2, excuse me, 3 U3W3 and 3 V3W3. And we can group some stuff together. And realize that that is the inner product of U with W. And that second grouping is the inner product of V with W. And why do I keep putting closing parentheses instead of closing angle brackets? All right, so we have the property of additivity taken care of. We next want to look at the property of homogeneity. So we want to take KU with V, which is going to be KU1 V1 plus 2 KU2 V2 plus 3 KU3 V3. And then using the distributive property of real numbers, we can factor out the k. And realize that this is k times the inner product of u and v. The positive definite property is a little bit more annoying because it has two parts. The first part is pretty easy. You take the inner product of u with u, you get u1 squared plus 2u2 squared plus 3u3 squared. And since u1, u2, and u3 are all real numbers, squaring them gives you results that are bigger than or equal to 0, and adding together a bunch of stuff that's bigger than or equal to 0 gives you something that is bigger than or equal to 0. That's the easy part. We also have to show that if you take the inner product of the 0 vector with the 0 vector, you get 0 squared plus 2 times 0 squared plus 3 times 0 squared, which is equal to 0. That's also not too bad of a part. But you also have to show that if the inner product of u with u is equal to 0, that's the same thing as u1 squared plus 2u2 squared plus 3u3 squared is equal to 0. That there are no non-zero ways of going about it. And that's always a little bit challenging to prove. We are going to take the stance of assume that u1 is not equal to 0. Well, we can rearrange and get that u1 squared is equal to the negative of 2u squared minus 3u3 squared. And again, because the squares of numbers are positive, if you subtract 2 times a positive number and then subtract 3 times a positive number, you're going to end up with a negative number. And since u1 is non-zero, that means that u1 squared is less than 0, which is false. And so by contradiction, we assumed that u1 was non-zero. We got that it was negative. I'm sorry, we got that its square was negative, which means that u1 was an imaginary number in the first place. And that's certainly not the case. And you can do the same thing to show that u2 being non-zero is nonsense and u3 being non-zero is also nonsense. All right, so if u1 not equal to 0 is false, u1 equals 0 must be true. I'm just going to say similarly, u2 equals 0 and u3 equals 0. It's the exact same proof. You assume that u2 is non-zero, you solve for u2, you realize that it's equal to a negative number. That's nonsense. And so you're good to go. All right. So the big takeaway here is that a vector space can have any number of different inner products, which is why it's important that we have that distinction between a vector space and an inner product space. A vector space is the rule of addition and scalar multiplication. An inner product space is the additional rule of an inner product. And any vector space can have any number of different inner products that might be useful in different circumstances. For one thing, that's a great way to make studying a vector space without thinking about an inner product space useful, because those properties carry to all of the inner product spaces. And it also becomes important that we distinguish and specify separately which inner product we are talking about when we're talking about a given vector space. So let's take a look at a different vector space. The other vector space we've been talking about a lot has been the polynomials of degree n. The usual, I should actually write these out a little bit more clearly so it makes sense. The usual inner product space, or the usual definition of inner product for the polynomials of degree n, is that the inner product of f and g is a naught b naught plus a1 b1 plus dot 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 plus an bn. Very similar looking to the inner product space for Euclidean vectors, or the Euclidean dot product, the one we are most accustomed to. But again, not the only one. Because this is so similar to the Euclidean product, I'm not going to go through and prove that it satisfies the properties of an inner product space. Instead, I want to look at something a little bit more exotic. The inner product on f and g we can define as the integral. We can actually pick any limits of integration we want, and this will still work. But my personal favorite is the integral from -1 to 1 of f of x times g of x dx. All right. All right, so we have the usual inner product. Sometimes it's called the canonical inner product. And then we have this one. Two separate inner products that we can define for the polynomials. Again, I encourage you to take the time to show that the canonical inner product actually does satisfy the properties of an inner product space. I'm going to take a look at the integral-based one because it's very interesting, a little bit different and a little bit of a different kind of thinking to get through this. Symmetry is fairly straightforward using the commutative property of multiplication on real numbers, which still works for real functions. We can swap that around, no problem. Additivity uses the linearity of an integral. Right? So you can use the distributive property to expand that multiplication. You can use the linearity of integration to split this integral up. And then you can recognize that those are, in fact, the inner product of f with h plus the inner product of g with h. Homogeneity, similar prospects. Scalar factors can be factored out of an integral. Leaving behind the inner product of f and g. Once again, positive definiteness, really the one that is a bit of a challenge. If I take the inner product of f with f, that's the integral from -1 to 1 of f squared of x dx, or f of x squared. And so we are integrating something that is always positive. And when we are integrating something that is always positive, that gives us good hope that things will work out nicely for us. If we're adding together a bunch of stuff that's always bigger than 0, the result is something bigger than 0. The integral of 0 is, in fact, 0. That works out pretty nicely for us. And then the tricky part assume that the inner product of f with itself is 0. That means that the integral from -1 to 1 of f squared of x is in fact equal to 0. And then using the fundamental theorem of calculus. Remember, the fundamental theorem of calculus says that the derivative of an integral is the integrand. So the derivative of the integral of f squared of x is just f squared of x, and the derivative of 0 is 0. And if a function is, if the square of a function is always 0, then the function itself is also always 0. All right, so we've got a couple of interesting inner product spaces that we can look at. We now have any number of weighted inner products to deal with for the Euclidean vectors. We have two very different looking inner products to deal with for the polynomials. And it's kind of interesting how those differences can give us some very different possibilities once we start trying to use these things. In the next couple of videos, we will be talking about the inner product standing on its own, but for right now, I want to take a look at an idea that builds off of the inner product. This is what we use more often. The norm of a vector is denoted double line absolute value bars on V is simply the square root of the inner product of V with itself. By positive definiteness, we know that the inner product of V with itself is positive, so the square root is defined, giving us a real number. A couple of properties of the norm. For any inner product space, the norm of V is always greater than or equal to 0. The norm of V is equal to 0 if and only if V itself is the 0 vector. And the norm of K times V is equal to the absolute value of K times the norm of V for any real number K. The first two are fairly straightforward. The last one, also not that bad, but kind of interesting. So I encourage you to take a minute and verify for yourself that result. The norm of K times V is the absolute value of K times the norm of V. It's one to play around with. Another theorem on norms. This one is important enough. It has a name, the Cauchy-Schwarz inequality. Cauchy, one of the most prolific mathematicians of all time. His name is pronounced Cauchy. Schwarz, somewhat less prolific, but his name is a little bit more obvious. So the Cauchy-Schwarz inequality tells us that the absolute value of the inner product of U and V is less than or equal to the magnitude of U times the magnitude of V. There's a written out proof of the Cauchy-Schwarz inequality in the textbook. You're welcome to take a look at it. Quite frankly, I don't think that it is all that interesting. It's very technical and doesn't gain a whole lot. And in fact, for the most part, the Cauchy-Schwarz inequality is not that useful, except that a direct consequence of the Cauchy-Schwarz inequality the triangle inequality is one of the most important things in mathematics. You first encounter the triangle inequality looking at actual triangles, where it's described as the length of one side of the triangle must be less than or equal to the sum of the lengths of the other two sides. In vectors, in 2- and 3-dimensional vectors, you learn that talking about that in terms of vector addition is also valuable. And here we claim that that works actually for any inner product space. As soon as we define the norm, the triangle inequality is going to hold. And the proof of the triangle inequality is very straightforward, except for the fact that it relies on the Cauchy-Schwarz inequality. But I love the proof of the triangle inequality. It's one of my favorite tricks in mathematics. It's to analyze the thing we care about slightly indirectly. And it turns out that we don't really know a lot about the norm of u plus v, but if we square it, we realize that this is the inner product of u plus v with itself. And then we can use the properties of inner products to expand that out. And we can use the properties of inner products to expand that out. And then notice we have an inner product of u and v. We have an inner product of v and u. The symmetry of the inner product lets us rewrite that. And then u plus v, inner product of u and v plus the inner product of u and v is simply twice. The inner product of u and v. Inner product of u with itself is the norm of u squared inner product of v with itself is the norm of v squared. That piece in the middle is a little bit trickier. That's where the Cauchy-Schwarz inequality comes in. Inner product of u and v is less than or equal to the magnitude of u times the norm of v. That's the Cauchy-Schwarz inequality coming into play. Then from here, we have a perfect square trinomial. This thing factors. It's going to be magnitude of u plus magnitude of v squared. All right, just noticing that that's the form of the perfect square trinomial with magnitude of u and magnitude of v instead of a and b that you're used to, or x and y that you're used to. And then finally, if magnitude of u plus v squared, I wrote that backwards. Parentheses go on the inside, square goes on the outside. If magnitude of u plus v squared is magnitude of u plus magnitude of v, the whole thing squared, then it must be the case that the magnitude of u plus v is less than or equal to the magnitude of u plus the magnitude of v. There is one other thing to talk about with the idea of the norm and the inner product here, and that's the idea of distance. As soon as we have a norm, we can define a distance based on the norm of the difference between two things. I'm not that worried about distance in this course, so I'm not going to go into that in too much depth, but I do like to at least mention that that's a thing before I wrap up. So take a look at some of the practice problems involving the inner products, the definition of the inner products, the norm, properties of norms, and some things involving the Cauchy-Schwarz inequality and triangle inequality. And I'll see you in the next video.